Okay, so having seen a lot of theory and kind of general hand-waving generalities in the previous video, let's get our hands dirty and actually calculate some best responses in Nash equilibria. So let's start with the most famous example, which is prisoner's dilemma. So here, I've drawn one of these diagrams again where I have one node for each pure strategy profile. So if you remember last week, I was drawing diagrams like this for dominant strategies, where the arrow meant that the target, for Pareto optimality, where the target was Pareto dominating the source. So here I repurposed the same kind of diagrams to mean something different. So now the arrow means that the target profile is a best response to the source profile for both players. So here, for example, this arrow means that D is a best response to player 1 against the strategy profile DC, and D is a best response for player 2 to the strategy profile DC. So that is to say, D is the best response given that D is best response for player 1 given that player 2 is playing C, and D is best response for player 2 given that player 1 is playing D. Whereas before, the rule for reading off the Pareto optimal strategy profiles from a diagram like this is any node that isn't the source of any outgoing arrow. Here is different. So if you remember that the rule to be a Nash equilibrium, the definition is that you have to be a best response to yourself for both players. So here, the Nash equilibria in pure strategies are any node that points to itself when you do this. So here in prisoner's dilemma, we find that both players defecting is the only Nash equilibrium. So the reason why prisoner's dilemma is such a famous example is, if you remember, the Pareto optimal strategy profiles are everything apart from DD. And then on the other hand, DD is the only Nash equilibrium. So here we have a case where you have some Pareto optimal strategy profiles and some Nash equilibria, but there are none in common. So you have a kind of conflict between individual optimality and group optimality. And you can think about what this means by putting yourself in the shoes of the players. So imagine that your starting strategy profile is CC. Given that player 2 is playing C, player 1 would like to unilaterally deviate from C to D, because then they increase their payoff from 2 to 3. But player 2 would also like to unilaterally deviate from C to D, because then they increase their payoff also from 2 to 3. But if both players do that simultaneously, then they end up here and they end up worse off. So here, kind of thinking about unilateral deviations is making life worse for both players. Okay. So you might think that you can calculate Nash equilibria by drawing a diagram like this and following the arrows. Unfortunately, in general, that doesn't work. So here's what the same diagram looks like for matching pennies. And here we get a cycle. So none of these nodes points to themselves. So it turns out that matching pennies has no Nash equilibrium in pure strategies. So if you think, say we're in the strategy profile HH, and so player 1 is happy. They don't want to unilaterally deviate away from H, because that would decrease their payoff from 1 to -1, whereas player 2 does want to deviate from heads to tails, because then they go from -1 to +1. So that takes us here. But once we're here, now player 1 wants to deviate to here. And so we go in a loop. So we have no Nash equilibria in pure strategies. But remember, Nash's theorem says that we have to have at least one Nash equilibrium in mixed strategies. It turns out that matching pennies has exactly one Nash equilibrium, which is that both players play heads or tails with probability 1/2. That is to say, they flip a coin. This should be intuitive if you think about how you actually play rock, paper, scissors in real life. Namely, you would play rock, paper, or scissors with probability 1/3. This is how people actually play, at least if they're amateurs. And mixing probability 1/3, 1/3, 1/3 is in fact the Nash equilibrium of rock, paper, scissors. Okay, so the lesson here is that following the best responses in general doesn't lead us to a Nash equilibrium, unfortunately. Things are more complicated than that. So you might wonder, a slightly more advanced version of this idea is, can we find Nash equilibria by gradient descent on expected utility? And the answer is no, if you do it naively. If you think of the mixed strategy profiles for matching pennies form a square like this, and if both players do simultaneous gradient descent, let's say each player simultaneously deviates in the direction of their negative gradient, you end up getting cycles like this. And the unique Nash equilibrium is here at the center of this circle, which is the unique point that's fixed by this this rotation. So that's the point that has converged. But if you pick a random starting point and then you follow the gradient descent curve, you will just cycle, you will not converge to here, unfortunately. So finding ways to make this kind of idea actually work in practice is actually a current research topic. Okay, let's do some more examples. So here is Stag Hunt. In Stag Hunt, we find that the two coordinated pure strategy profiles are Nash equilibria. So both players hunt stag is Nash equilibrium, both players hunt hare is a Nash equilibrium. The two discoordinated strategy profiles, the best responses will cycle between them. And in chicken, we get kind of the opposite thing, that the two discoordinated strategy profiles where one player goes straight, one player swerves, these are both Nash equilibria, whereas the two where both players go straight and both players, this is both players go straight, this is both players swerve, these cycle. So imagine both players are going straight, both players would like to unilaterally deviate to going straight, because then they go from 0 to 1, but if they both do that, then they crash and die, and vice versa. Okay, so both of these games have two pure strategy profiles, and I think both of these will have at least one other mixed strategy profile. I haven't worked those out. Here's one I have worked out. So this is Battle of the Sexes. So here we get the same kind of diagram. This is actually the same diagram as Stag Hunt, where the two coordinated strategy profiles, these are both Nash equilibria. So these are the two where both players go to the same place, and then the two anti-coordinated ones, these cycle. So we get two pure strategy Nash equilibria. So this one has exactly one more mixed Nash equilibrium, where player one's strategy is to play F with probability 3/4 and B with probability 1/4, and player two's is the opposite, F with probability 1/4 and B with probability 3/4. So if you work this out, it turns out that given these mixed strategies, neither player can increase their expected payoff by unilaterally deviating. So in small examples like this, you can actually work these out. It's only kind of algorithmically hard in general. In specific cases, you can do it. For example, you can solve a game like this by linear programming. I did not solve this by linear programming. The way that I got these numbers was I put this game into Gambit, and Gambit has built-in functionality to calculate Nash equilibria. So I will not be asking you to calculate these by hand. I will be asking you to do this kind of thing using Gambit.